Okay, I think people can hear me. I move here, okay. So the starting point of this paper is actually a classical observation, which is that actions convey information. So the famous example is span signaling model, in which credentials convey information about the ability of a job applicant. There are lots of other examples. Waiting in line conveys information about the willingness to pay of a customer. Physical activity conveys information about the health status of an individual. For example, consider the following quote from Joseph Stiglitz, who has famously thought a lot about insurance markets. He said, an insurance company might realize that by locating itself on the 5th floor of a walk-up building, only those with a strong heart will apply. More subtly, it might recognize that how far up it needs to locate itself depends on other elements of strategy, such as premium charge. These actions are often costly in that they're socially wasteful. Yet, because the preferences over these actions are correlated in some way with the private information that affects the allocation of the productive assets, they could be useful for screening. This raises the question, when should we expect these costly non-price instruments to be used in the design of optimal mechanism? And this question goes back at least as far as Spence 1973, when he writes non-price signaling and screening, economic and social contexts deserve more attention, in spite of the fact that they're frequently inefficient. The key difficulty of this problem is its multidimensionality in two fundamental ways. First, there are going to be multiple instruments. There's the price instrument, and there's the non-price instrument. And there are also going to be multidimensional pair of information. For example, the buyer is going to have a private value for the good and a private cost for waiting in line. So in this paper, we studied this question, the effectiveness of costing instruments in a general multidimensional screening model that consists of two additive components. So there is going to be a one-dimensional productive component which the principal intrinsically cares about, such as insurance coverage. And then there is going to be a costly component which the principal may utilize to help screen but destroy social surplus, such as walking upstairs. The costly component itself can be multidimensional, as it will be clear from the model. More specifically, the principal designs a mechanism that assigns the productive allocations in a one-dimensional space, call it X, and the costly actions in an arbitrary space, call it Y. Monetary transfers are going to be allowed. Nonlinear and interdependent preferences are also allowed. By interdependent preferences, I mean that the ex post payoff of the principal can depend directly on the realized debit of the agent, such as in labor market or insurance market examples. So the main result of the paper is a theorem that roughly states the following. If the agent has preferences that are possibly correlated in a suitably defined sense between the two components, then simply screening the productive component is optimal. That is, the costly non-price instruments are optimally never used. And as you can see, there is a quotation mark around positive correlation, because part of the result is also to find the right definition for what it means for the agent to have possibly correlated preferences between the components. We're also going to show a partial converse in the sense that for a given negative correlation structure, there exist utility functions such that the optimal mechanism must use these non-price cost instruments. To fix the idea, let me just classify the leading examples by the structure of their correlation. So first, think about the labor market screening example. There, the principal is the firm, the agent is the job applicant, because of the productive allocation is the work allocation, and then the costly action is, say, credentials, exams, interviews. Because a higher ability applicant tends to find both work easier and also exam easier, the preferences are possibly correlated in that example. Now, if you think about the insurance example proposed by Stiglitz, there the productive allocation is the insurance coverage, and the costly action is some physical activity like climbing the floor. There, the type who has higher willingness to pay for the insurance tends to have higher risk. Those are exactly the types who tend to find climbing the floor harder. So the preferences are negatively correlated in that example. There are also examples in which the correlation may go both ways, like the waiting line example. Now, the mean result is an abstract result, as you will see momentarily. However, using that result, you can obtain implications in other multidimensional mechanism design problems that may initially seem quite different from my framework. For example, consider the canonical multiple good monopoly problem, which you just saw. There, every good is generating surplus, which seems quite different from mine, because in my framework, I would require there's only one dimension that is productive. However, suppose you take a different point of view. In particular, think about removing items from a given bundle as a costly action, and doing kind of a transformation of the action space. You can map that problem into my framework. In particular, you can obtain results on the optimality of pure bundling, which recovers the result of Nima and JSON. You can also obtain new results on the optimality of bundling with quality discrimination and optimality of bundling with a menu of nested bundles. In a different setting, you can consider monopolies selling over time to consumers who has both private value and private discontinuity. Because delay is also costly, you can apply my framework and show that obtain results on how the probability of intertemporal price discrimination depends on the correlation between the willingness to pay and the patience of the consumers. Okay, with that, let me just jump directly into the model. So the model is going to consist of two components. I will always use superscript A to indicate the productive component and superscript B to indicate the costly component. And in case you get confused, B stands for bad and hence costly. The productive component is a one-dimensional component. It has a one-dimensional allocation space, script X, one-dimensional type space, theta A. And then I will always use U to denote agent's utility function and V to denote principal's utility function. So both are assumed to be continuous on the product space on the productive component. And then the costly component is going to be a multidimensional component, both that the allocation space, script Y, is arbitrary abstract measurable space, and the type space theta B is a compact subset of a finite dimensional Euclidean space. Both the principal and agent's utility function and costly component are allowed to be any-bounded measurable functions. I'm going to assume that the preferences are additively separable across these two components and quasi-linear in the transfers, as displayed on the slide. I will use theta without a superscript to denote the product of theta A and theta B, little theta as an element of it. The principal is going to have a Bayesian prior over the types denoted by gamma. I will use SA and SB to denote the surplus function on the productive and costly component, which are simply the sum of UA and VA and the sum of UB and VB. And the costly component differs from the productive one because it doesn't generate surplus. So SB is always non-positive for all theta B and all Y. I'm going to assume there is an element Y0 in the space of Y that represents no costly screening, i.e., when you plug in Y0 into either the agent or the principal's utility function, you get back to 0. And here's our screening problem. A mechanism is a measurable map that maps a reported type to an assignment of a productive allocation, a costly action, and a monetary payment that satisfy the usual incentive compatibility and individual rationality constraints as displayed on the slide. The principal is going to maximize over the space of mechanisms her expected payoff. We say a mechanism XYT involves no costly screening if Y maps all theta to Y0 and XT does not depend on theta B. So this is equivalent as saying that the mechanism screens only the productive component. So I will need some assumptions on the structure of the preferences, and here is the assumptions I need on the productive component. First, I'm going to assume that the agent's utility functions UA is non-decreasing on the type and has strict increasing differences. So the first two conditions are completely standard, also known as the Spencer-Merlis condition. The third condition is a new one. It is a condition imposed on the surplus function on the product component. I'm going to assume the surplus function satisfies a single crossing differences condition. I will refer to this as the surplus condition. It turns out that this is satisfied in most applications. In particular, if the principal does not have interdependent valuations, then this condition has no bite because it is implied by the second one. If the principal has interdependent valuations, then this generally differs from the Spencer-Merlis condition. I will explain why this matters momentarily and give you a counterexample when this fails. Now here is my definition of positive correlation preferences. First, I'm going to assume that the utility of the agent on the cost component is non-decreasing in the type theta B, so that higher theta B actually represents the strength of the preferences. And then I'm going to assume that theta A and theta B are positively correlated in the sense that the conditional distribution of theta B conditional on theta A shifts upward in the sense of stochastic dominance when you shift theta A upward. So here is the mean result. Suppose these two assumptions hold, then there exists an optimal mechanism that involves no costly screening. That is, screening only the product component is optimal. And because the product component is one-dimensional, the optimal mechanism here can be explicitly characterized. Now here is the partial converse stated in an informal way. Suppose for some dimension I, which is one of the costly dimension, theta I is strictly negatively correlated with theta A, then there exist utility functions such that any mechanism screening only the productive component is strictly dominated by a mechanism that involves costly screening. I don't think I would have time for the proof, but let me give you a sequence of examples just to illustrate the basic intuition and the main difficulties for the proof. So let's go back to the opening example where there's a principal selling insurance to a buyer who potentially has two types, a low-risk type and a high-risk type with equal probabilities. I'm going to assume that the low-risk type has a value of 2 for the insurance, which is represented by X, and high-risk type has a value of 3. It costs 0 for the principal to serve the low-risk type, but it costs a lot, say 4, to serve the high-risk type. So these parameters are chosen such that there is enough adverse selection in the market. Without any costly instruments, the principal can do no better, so simply not trading. Now suppose we're in Stiglitz world, where the costly action itself is climbing the floor, which the low-risk type I'm going to assume has 0 cost, but the high-risk type has a cost of 1. And the principal intrinsically doesn't care about whether the agent climbed the floor or not. And as I mentioned earlier, this is a negative correlation case because the high-risk type likes the insurance more and finds climbing the floor harder. Now, because of this negative correlation, the principal can use it to deter the adverse selection. In particular, just offering a menu of a single option that says that I'm going to offer you the full coverage plan at a price of 2, but in order to be eligible for that plan, you have to climb the floor. And because the high-risk type finding climb the floor hard, they wouldn't try to get this option, and the principal can get strictly positive payoff. So notice that in this example, it violates both the positive correlation assumption and the surplus condition I imposed earlier because it's very costly for the principal to serve the high-risk type. Now, suppose, this is the second example, suppose the costly action is waiting in line instead of climbing the floor. The story here is that a high-risk type agent would have a harder time to be employed and therefore has lower value for time. So in particular, I'm going to assume that they have 0 cost for waiting, but the low-risk type actually has a cost of 1 for waiting. So I'm flipping the cost structure, and therefore this becomes the positive correlation case. But I didn't change anything about the productive component, so this still violates the surplus condition. As I alluded to earlier, the cost instruments can still be useful. For example, consider the following menu with 2 options, which essentially says that I'm going to offer you a full coverage plan at a high price of 2, but require no waiting. And then I'm going to offer you a second option, that's a low coverage plan at a very low price, 1/2, but requires some amount of waiting. Under this menu, the low-risk type, finding waiting too costly, will pick the first option. And high-risk type, finding low coverage plan cheap, picks the second option. And with this self-selection, if you do the calculation, the principal can get 1/4, which is also strictly bigger than 0. Now, let me slightly modify the previous example by changing the cost of serving the high-risk type from 4 to 2.5. So I did not change any of the payoff for the agent, so the set of incentive-compatible mechanisms is exactly the same. In particular, the previous menu induced the same self-selection. And if you do the calculation, that would yield a payoff of 5/8 for the principal. But this is no longer optimal. In particular, simply selling to both types would give you a payoff. So without any costly instruments, simply selling to both types will give the principal a payoff of 3/4, which is strictly bigger than 5/8. So compared to the previous example, this example now satisfies my surplus condition. This does not change any of the implementable outcome, but it turns out to affect which ones are optimal. In particular, the ones that do not use the cost instruments become optimal. Let me just summarize a little bit from these examples. So as in most multidimensional screening models, the main difficulty comes from the fact that when you add an additional instrument, it significantly expands the space of implementable outcomes. In particular, from those examples, you can see that the insurance coverage allocations are not monotone in the type, which can never happen in any one-dimensional mechanism. And if you compare the second and third example, you can see that the implementable outcomes stay exactly the same. But in the third example, the cost instruments are not used. Therefore, the proof must deal with this richer space of mechanisms. And how do we do that? Well, a key observation is coming from comparing example 1 and 2. So in example 1, when there is negative correlation, recall that we're adding the costly action, which is climbing the floor, to the option that's targeting the low-risk type. And it's used to deter deviation from the high-risk type to the low-risk type, which is the downward deviation. And in the second example, under the positive correlation case, we're adding the costly action to the option that's targeting the high-risk type. So that is used to deter the deviation from the low-risk type pretending to be the high-risk type, which is the upward deviation. So this turns out to be a very general phenomenon and one of the main ingredients of the proof. How much time I have?
Let's say 2
Okay, let me just say a little bit about proof.
I mean, you can confirm the
Okay. So, sure. So let me just give a very high-level sketch of the proof with a picture. So on the left panel, I'm drawing a two-dimensional type space. The x-axis is the productive component, the y-axis is the cost component, and the gray area kind of represent the positive correlation. So at very high level, the proof is by contradiction. So for a given incentive-compatible mechanism that uses these costly instruments, I'm going to construct various sequence of steps, an alternative mechanism that doesn't use the cost instrument and strictly improves upon the previous one. So let me just fix any incentive-compatible mechanism. So the first round of modification is use the idea of compensating variation. So suppose I fix the assignments of the productive application, which is x. I'm going to shut down the use of costly instruments, make every type get y0. I'm going to adjust the transfers in such a way that each type gets exactly the same payoff as in the previous mechanism if they report truthfully. So this will increase the total surplus because the instruments are costly, and because I'm holding the agent's utility fixed, this must increase the principal's payoff, assuming the agent report truthfully. Of course, there's no reason for the agent to report truthfully after you do this modification. This can break a large set of IC constraints, but it still preserves some of them. In particular, it preserves all the downward IC constraints on the costly component. And this uses assumption 2.1, that is higher theta b represents that the agent likes the costly action more. Now, I claim that the positive correlation assumption essentially translates the downward IC constraints from the costly component to the downward IC constraint on the productive component. For the simple case, just think about this as a monotonic path. And in this case, the downward deviations are exactly coupled in this deterministic way. So that's why the IC constraints from the costly component translates to the productive component. For extra joint distribution, you can write down that joint distribution as a mixture of this kind of monotonic path and apply the argument path by path. And this uses our assumption of positive correlation and the classical result of Strasson's coupling. Now, after all this, what you get is a mechanism that does not use costly instruments and satisfy all the downward IC constraints. So in the last step, there is another round of modification where I'm going to modify both x and t in such a way it becomes a fully incentive-compatible mechanism while not decreasing the objective. So the last step is the most challenging one. It's proved by a variational argument, and it uses all the assumptions we put on the productive component, in particular the surplus condition. With that, let me just conclude. So we have studied the effectiveness of cost instruments in a multidimensional screening model. We have seen quite generally the positive correlation of agents' preferences imply that the optimal mechanism screens only the productive component. And I didn't show you formally, but you can look into the paper. Application of this framework can provide insights on other multidimensional mechanism design problems, such as bundling or intertemporal price discrimination. OK.
All right. We have time for one or two questions.
Yes.
So you said you have a result describing when nested bundling is optimal?
Yes.
Is there an informal or intuitive way to describe when that happens?
Yes. So, OK. It's going to be a little bit hard to describe.
Can you repeat the question fully for the virtual audience?
Can you repeat the question?
OK, yeah. So the question is whether there is an easy way to describe the conditions under which bundling with a menu of nested bundle is optimal. I don't think I can describe in one sentence.
You can do 2 sentences.
OK. I think basically it's this. So that result applies when you have the monotonicity condition as in your paper. So there's one-dimensional type. And then suppose you have only 2 goods. And then suppose I increase the type. And then the incremental value of one good compared to the one increase, and the incremental value of one compared to the other decreases. So essentially, it's that condition. I hope this is helpful.
Makes sense.
Yeah. OK, thank you.
Let's thank Frank again.